going to speak about joint work with them, which is about flexible polyhedra. So we all know that almost all polyhedra are rigid. So like this, the first result in this direction was by Cauchy, that all convex polyhedra are rigid, and then Gluck showed that all simply connected polyhedra, almost all simply connected polyhedra are rigid. But thanks to Bricard, we know that there actually exists polyhedra that are flexible, and also later Bob Connelly gave an example of embedded flexible polyhedra, which was I think on 18 vertices, and then Steffen's introduced polyhedra, which is embedded flexible but only on 8 vertices. Sorry, 9. Yeah, I think 9. Yeah, so let me start with the most known flexible polyhedra. So I switch to an animation of polyhedra by Bricard, which is actually an octahedron. And Bricard classified all flexible polyhedra. So the first type is line symmetric, where pairs of vertices of this octahedron are line symmetric, and just by counting parameters and due to symmetry, such octahedron can flex, as you can see on the animation. Another type of Bricard's flexible octahedron is with plane symmetry. So the whole framework is plane symmetric. And again, just by counting parameters, one can see that or show that such a framework, or if you see this polyhedron as framework, is flexible. And there's also a third type that is not symmetric, and it's described in various ways, but let me for now just show you an animation of this third type, and then I switch to my slides. So here we can see how it flexes, and actually it has two flat poses, this third type of octahedra. So I have here again two pictures of the first two types, and what I would like to point out is that if now we look at 4 cycles in this octahedra, and we look at the 4 cycles that have no diagonal, so in both pictures they are indicated by that they have same color. So like we have this red 4 cycle, blue 4 cycle, and green 4 cycle. So these are actually all 4 cycles that we can find that have no diagonal in octahedron. And what we can do now is that if such an octahedron is flexible, and we look at, for instance, at the green one, and we denote the edge lengths, we get that we have the opposite edge lengths are the same by the symmetry. And again, here we have B and B. So it's rather trivial that we can sum up the edge lengths with some signs in a way that we get 0. So of course, like if we put for one B plus and for the other minus, and the same for A, they sum up to 0. So this is somehow a trivial zero-sum cycle where I'm heading in more general situations for general polyhedra. And of course, because of the symmetry, we can do the same also for the type 2. So here we can take the edge lengths and assign them signs in a way that they sum up to 0, but it's fairly trivial, or it's trivial because of the symmetry. We have 2 edge lengths that are the same. So if we look at the type 3 of Bricard octahedron, sometimes it's described using some construction from one of its flat poses. So you can look at Bob's camera to see one of these flat poses, and maybe he can also show how it flexes, or I don't know whether it's flexible or not, his construction. Yeah, it is. Thank you. But in another work with Josef, Matteo, and Georg, where we reproved Bricard's classification of flexible polyhedra. We use a slightly different description of this third type, which is, let's say, more algebraic. And it's in terms of equations on edge lengths and some restrictions on angles. So let me just first describe the what are the conditions on angles. So if we look at the the pyramid in our octahedra, so like we just remove one vertex from the octahedron, and what is left is a pyramid. Then the two opposite angles either have to be equal or they have to be complementary, and it has to hold the same for the other pair of these angles for every pyramid. So that's one kind of algebraic conditions we get for this third type. And the other type is formulating using this zero-sum cycles. So here on the right, you can see 7 possibilities that one can get if you remove all the symmetries of the graph. And the condition is such that if you look at 4 cycle without which is induced, so it doesn't have diagonal. So these are this blue, green, and red 4 cycle on the left. There has to be an assignment of signs such that if you sum up the edge lengths with these signs, you get a 0. So how the picture works, if you look, for instance, at this visualization of how the edge lengths should be assigned, for the outer 4 cycle, I indicate that the 2 light green edges they are, let's say, with the plus sign in this 0 sum, and the 2 dark edges are with the minus sign. So if I put them A, B, C, and D, I have a condition that A plus B minus C minus D equals 0. And for this type 3, we have such a condition for all 3-4 cycles that are induced in the octahedron. And the picture somehow shows all the possible combinations that one can get, how these signs are assigned. So of course, in every 4 cycle, we have 2 plus and 2 minus signs, because if we have, let's say, 3 minus signs, then the 4 cycle would degenerate into a line. So it's always 2 and 2. And actually, these 4 cycles for octahedra were already studied by Legerský. So the paper is in French, so I'm not sure like how much he considers all the possible cases he can have, but at least for some cases he studies flexibility, having this condition on 4 cycles. So that was short example using Bricard octahedra. So before we go to some other examples and previous results, let me just briefly recall the definitions we use. So by triangular polyhedron, I mean an abstract, finite, 2-dimensional simplicial complex, such that every edge belongs to exactly 2 faces. So there is no boundaries, so it's a triangulation of a closed surface, and I can realize this polyhedron using the terminology of rigidity theory. So I take the one skeleton of the polyhedron, namely the vertices and edges, and I realize the edges in the space, so that the I require that adjacent vertices are mapped to different points. So it's a bit less strict and we require injectivity. So this is sufficient. So in other words, the distances between adjacent vertices are non-zero. So edge lengths are always positive. And if I have a realization, such a realization induces edge lengths for the edges of the polyhedron just by taking the Euclidean distance between their endpoints. And we study flexible polyhedra, so I should say what is a flex, or to be more precise, I could say a non-trivial flex is a continuous map from an interval into the space of all realizations, such that the flex starts at my given realization of my polyhedron. I want the flex to preserve the edge length. So every realization in the flex has to have the same edge length as the starting one. In other words, it means that the faces are preserved because I have triangular polyhedron. And the third condition is that I want to have something non-trivial. So I want to have a non-trivial flex, so it's not induced by a reached motion. So if we study some other examples of zero cycles, there is the case of suspensions. So a suspension is a cycle together with top vertex and bottom vertex, or north and south, which are linked to every other vertex on the cycle. And this cycle is called sometimes the equator of the suspension. And Bob Connelly showed in 1974 that if a suspension is flexible, there is a sign assignment to the edges on the equator, such that if we sum up the length of these edges with these signs, we get 0. So the result is a bit hidden in the draft, an attack on rigidity. So that's maybe one of the reasons why Mikhailev didn't notice. And so he wrote a paper in Russian where some of this statement is written explicitly in Mikhailev's paper, not in Bob's paper. But yeah, it can be like easily seen from the original one. So they show that there exists a cycle with assignment of signs, such that when we sum up the edge lengths, we get 0, but only for suspensions. So we want to do something for any polyhedron. So before I state our result, there is also a result by Alexandrov, only from 2 years ago. So he considers an oriented polyhedron with triangular faces that is flexible. And he can show that if you pick an edge such that the dihedral angle at this edge changes along the flex. So that means that like you have these two triangles, you have this edge E, and the angle between these two faces changes along the flex. Then the length of this edge is a rational combination of the length of the remaining edges of the polyhedron. So what we can do is that we can forget this assumption that the polyhedron is oriented. So for us, it works for any polyhedron. And we say much more about how this Q-linear combination of the lengths looks like. Namely, we really produce a zero-sum cycle. So our theorem says that if we now assume just a triangular polyhedron that is flexible, and we fix an edge of this polyhedron, and the dihedral angle at this edge changes along the flex. So that's the same what Alexandrov assumed about the dihedral angle. Then there actually is an induced cycle of edges that contain our edge E, and there's a sign assignment such that if we sign the edge lengths with these signs, if we sum the edge lengths with the signs, we get a 0. So of course, this is obviously Q linear combination of the remaining edges of the polyhedron. like in Alexandrov case, but we know which edges, and we know that it's actually not a combination with coefficients from the rational numbers, but just plus and minus 1. So if we now look again at the Bricard octahedron, actually just from this theorem, we indeed get that these 3-4 cycles, they have to satisfy this zero-sum condition, because in any flexible octahedron, every dihedral angle has to change. And if I pick an edge whose dihedral angle changes, then there is only there's a unique cycle that is induced and contains this edge. And so just by taking all the edges, we get 3 conditions having 3 having 3 zero-sum cycles. Yeah. Let me maybe just return for a moment to these suspensions. The octahedron is a suspension, so the theorem holds also for octahedron. And actually, Bob Connelly showed that there might be even like stricter conditions that we don't sum over the whole cycle, but there is some partition, and we sum up over the edges only. In each part of this partition, we get zero sum, which is something that we could see for the symmetric case of Bricard octahedron. Okay, but like in our case, we construct a cycle, and we prove the existence of the signs, so that we get a zero-sum cycle. So I would like to give you some brief idea how the proof works, or somehow how is the general strategy. And before doing this for construction of zero-sum cycles, I would like to advertise a bit our also some of our previous work, because it somehow follows similar scheme or similar framework. So like the 3 situations we've considered are the planar frameworks, like which is indicated here, then spherical frameworks, and then this flexible polyhedra. And the general strategy one can try to get some combinatorial conditions on the flexibility is to consider some compactification of the space of realizations of this particular linkage. So like for planar frameworks, one can consider this product of projective spaces. For the sphere, we considered the moduli space of stable curves of genus 0 with n marked points, where n is twice the number of vertices of our graph. And in this case, for polyhedron, for polyhedra, we consider a Möbius model, which I will describe on the next slide. So, and once we have our compactification, because we assume that we have a flexible mechanism, then we have infinitely many realizations or infinitely many points in our compactification. And we can take Zariski closure of these infinitely many points. And because these spaces are projective, the curve, or we can either have something higher dimensional, but let's assume that we have just a curve in this space coming from the realizations. This curve intersects the boundary of the space in some sense. So of course one has to specify what this boundary is, but we obtain some boundary points which usually do not correspond to actual realizations. So they really come from the closure that we do in the compactification. And using these boundary points, one can deduce some combinatorial properties about the original object. So in the planar case, we get neck colorings. So those are the edge colorings by 2 colors, such that for every cycle, either all edges are blue or all edges are red, or we have at least 2 blue and 2 red edges. For the spherical case, we get something that we call NEP coloring. That means no alternating path. So it's prohibited that we would have blue, red, blue, or red, blue, red path. So that's the case for the sphere. And by studying the boundary points for the Möbius model, in case of polyhedra, we get our zero-sum cycles. So for the first two cases, what we get is like purely combinatorial condition on the original graph. For the zero-sum cycle, there's also a bit of geometry in the sense that we know that we sum up we don't get just the signs, but we know that if we take the edge lengths with these signs, we get 0 in our sum. But also for the case of neck coloring and NEP coloring, if the procedure is done for a Laman graph or for some over-constrained graph, having this, if you somehow want this particular coloring to be so-called active, we can also deduce some polynomial constraints on the original edge lengths of our graphs. So it also gives some geometric restrictions. And another thing that works in all these three cases is that, like, if now I just forget about any framework and I take a neck coloring of my graph, I know how to construct a framework that is flexible using this neck coloring. Similar with the NEP coloring. And at the end of my presentation, I will also show that we can do something similar also with the zero-sum cycle. So it works. Not really that we would invert it, but we can construct something flexible having these combinatorial properties. Okay, so let's now forget about planar frameworks and spherical frameworks and focus on polyhedra. And the compactification we use for polyhedra is Möbius model or Möbius embedding. So in this case, we take our points in R3 and we map them to the projective space P4 by taking the x, y, z. Then we take the distance from the origin, and here we put 1. And now, if we take the image of the whole space R3, under this Möbius embedding, we know that the image lies on a hypersurface in P4 having this equation. So this is where, like in M, one of our vertices will live, and taking M to the power of the number of vertices, that will be our compactification space where we get our result for zero-sum cycles. What's important when one wants to construct this moduli space or compactification is that you need to know how the distance between points in the original space behaves in the compactification. And in this particular case, the square of the Euclidean distance between points U1 and U2 is given by the symmetric bilinear form that defines our hypersurface M. Now assuming that we dehomogenize in a way that the H coordinate is equal to 1. So that's how, yeah, having this formula, we can prove what we need about our objects. Yeah, and I mentioned in the general scheme that we are interested in infinite points. So here for the Möbius space for this set M, we consider the infinite points to be points that have the H coordinate to be equal to 0. And immediately one can see that if H is 0, then x squared plus y squared plus z squared has to be equal to 0. So there's only a single real point at infinity. So we denote it by omega infinity, which is 0, I'm sorry, I will put, not able to really make dots, so I will put just columns, but there should be, I will put 2 commas, but there should be count because we're in projective space, but it doesn't work on my tablet. So we have this 0, 0, 0, 1, 0 point, which is infinity. But yeah, that's the only real one. But the trick we do, that we did also in the previous cases, and we do it now, we consider our situation over complex numbers, because like the distance of the reals is defined algebraically because we take the square distance. So we go to complex numbers, and of course over complex numbers this equation has solutions. So we have some infinite points, and those that are not this this only real infinite point, we call them simple infinite points. And using these simple infinite points, we can see later how to get a zero-sum cycle. So let me restate our main theorem once more, introducing some notation. So the only thing I want to introduce extra now is some names for the vertices we are considering. So we have this W1, W2, that's our edge whose dihedral angle changes, and we denote this by N and S. And I will briefly show how to construct the cycle that goes through W1, W2, and the signs, such that we can, when we sum them up with the signs, we get 0. So what do? Like because every realization can be moved somewhere else by rigid motions, this would cause having infinitely many realizations that are congruent to each other. We want to get rid of those. But since we have a non-degenerate phase, we can just fix this phase to be at fixed position during the whole flex. And in this way, we get rid of the rigid motions. So that's somehow the first step. And now we take our flex that we assume. We use Möbius embedding to map the vertices in this flex, or the realizations and the vertices in this flex to our hypersurface M and superscript V, because each vertex is mapped to its own copy to the hypersurface M. And now, because there are infinitely many non-congruent realizations in the flex, this Legerský closure is at this one-dimensional because there are infinitely many elements in the closure. So it's at this curve, maybe something with higher dimension. So we can look at the copy of the hypersurface M that corresponds to the vertex S. So I draw again my image. So this W1, W2, N is now fixed. So the images under the Möbius embedding are finite, and this vertex S, since we assume that the dihedral angle changes along the flex, so the vertex somehow of the real state rotates around the edge, the corresponding component in the Legerský closure is at this one-dimensional, so it hits the infinite hyperplane. So there actually exists a point in infinity in this Legerský closure for the vertex S. So we call this element rho infinity. So now this is, so we pick it based on the vertex S, but that's actually a point in M to the V. So now this rho infinity serves us as this boundary point that we can use to deduce some extra information about the flex or about the geometry of our polyhedron. So we use this rho infinity to color vertices of our polyhedron namely, we color a vertex red if rho infinity of this vertex is a finite point in M. We color it blue if it's simply infinite with some extra condition that involves this S, where the condition you can see here, but I mean, that's important for the technical details of the proof, but not for now. And the rest we color gold. So if we look now at a small piece of some triangular polyhedron, we have vertices colored red, blue, and gold. And using the properties of the Möbius embedding, one can prove that actually it cannot happen that there would be a triangle with all three colors. So blue, gold, red triangles are prohibited. They do not occur. So what we do now is that we forget about the gold vertices and we look at the triangles that have at least 2 red and 1 blue vertex, or the other way around, 2 blue and 1 red. So either we consider triangles that look like this. So now we consider only these kind of triangles, 2 blue vertices and 1 red, or 2 red and 1 blue vertex. We forget about all the other triangles. So in my picture on the left, these kind of triangles, they are labeled by letters. And we construct a graph whose vertices are the triangles, and where 2 triangles are incident if they share an edge that has 1 blue and 1 red vertex. So for instance, like AB is incident here and here because they have this edge with blue and red vertex, and similarly for the other triangles here. So the triangles here, they correspond in my new graph whose vertices are triangles to this cycle. And yeah, one can easily see that in this graph on triangles, every vertex has degree 2. So it's just a union of cycles. So I pick a cycle that contains my my edge W1, W2. So it's in the picture here. It's this one. So I pick this cycle. And now I look at the blue and red vertices, and because I have a cycle, and one can actually construct a closed walk of red vertices and closed walk of blue vertices based on this cycle of triangles. So that's depicted on the right. And using the properties of Möbius embedding, we can prove something about the red vertices in my cycle. So I have a cycle, and the red vertices, they are, of course, in the Möbius model. At the same time, they are finite by definition of red vertex. And what is important is that they are in the tangent hyperplane to the point rho infinity S, which is like a crucial part using which bit technically one can show that if we have this red cycle, there exists a map from the set I mentioned on the previous slide to the complex numbers, such that the edge length between 2 neighboring vertices in my cycle is plus minus this map pi to the rho infinity of Vj minus rho pi rho infinity Vj plus 1. So we get that, I mean, it's either plus or minus. So now when we take integers or signs plus or minus 1, we can just assign the correct signs to each of these edge lengths here, such that it cancels the sign. So if there is plus, we assign plus, and if there is minus, we put minus. So this cancels the signs. And then we have just a telescoping sum. So like all the summands that they cancel out. So we get that it's 0. So this is how we get a cycle of edges with signs so that they sum up to 0. So it's also possible to generalize a bit. So in the theorem, as I stated before, we had that we get an induced cycle that gives 0 sum. We can tweak the proof or do some extra work that the cycle actually contains only edges whose dihedral angle also changes along the flex. So it avoids the edges that would stay somehow frozen during the flex. But here we need, so we lose the property that the cycle would be induced. And having this generalization, we can also prove analogous statement for non-triangular polyhedra. So we need some assumption that polyhedra is such that we can triangulate it in a way that we don't introduce any new vertex and all the triangles are non-degenerate. But having this, we can again find a zero-sum cycle. And to conclude, I promise that there is some kind of constructions also in the other direction. So now if I have the one skeleton of a polyhedron and I fix a cycle such that if I remove the vertices and edges of this cycle, it will separate this graph. And I fix a sign assignment for the edges of this cycle such that not all of them have the not all of them have the same sign. Then I can construct a polyhedron that is like pretty degenerate, but it has a flex such that the edges in this cycle, they change their dihedral angles during the flex. So like the construction is known, it's so-called butterfly motion. So the edges that have plus, I put in one direction, and those that have minus, I put in the other direction on a line. And of course I can adjust the length so that eventually when I close the cycle, I get back to the same point. And yeah, since the cycle, I assume that it separates the graph, somehow I get two parts that are on other sides of the line and they can rotate with respect to each other. So that's some of the backwards construction from assignment of signs to a cycle that separates the graph. Of course, not every cycle. So if the polyhedron is not homomorphic to sphere, then not a cycle doesn't necessarily separate the graph. So we need this extra assumption. Yeah, so that's all. Thank you.